Hello, good morning. Good morning.
Good morning, sir.
Good morning, everyone.
Morning, sir.
I'm sorry for starting behind schedule. This the car was just interrupted. In fact, they have brought it back. Anyway, we couldn't hold a lecture on Tuesday because of the reasons we all know. We couldn't agree on a time to meet on Tuesday. So today we want to look at want to start from where we stopped. Looking at the basic pulse and sequence. Basic pulse sequence. In MRI imaging, we often talk of so many pulse sequence. Which sequence do we want to use at a particular point in time that will give us the best image and to help us maximize contrast. So the key to choosing the best type of parameters is actually based on an understanding of the basic pulse sequence, which we are going to briefly talk about this morning. We should bear in mind we have basically two major pulse sequence. Every other one is actually a modification of these two pulse sequences. The spin echo and the gradient echo. At times, this one usually add a gradient recall. We get to know the meaning of this recall. Then the third one, which is actually not a new type of sequence, is the inversion recovery. Inversion recovery. Inversion recovery actually, like I said before, is not a kind of a pulse sequence, so to say, new pulse sequence, so to say. Actually derivable. You can apply inversion recovery to spin echo. You can also apply it to gradient echo. But be that as it may, we are going to look at these three major pulse sequences because everything we do in MRI depends on these pulse sequences. And today, in doing this, we need to understand what we mean by pulse sequence. And by hindsight, we are looking at, we look at the time of echo, time of repetition, and also very importantly, in angle, because these are the major components, the machine components or operator define the components that help us modify all these pulse sequences. So by way of introduction, we are going to look at these key terms: time of echo, time of repetition time, and the flip angle. What do you mean by pulse sequence? Pulse sequence is actually the series of steps we apply in getting an image, in getting an MRI image. Those steps we undertake, or the machine undertakes, such that we finally get an image. We finally get a detectable signal. Bear in mind that before we have a pulse sequence, it has to be chosen at a point in time that we maximize signal. Because at any point in time, you can actually get a signal from an MRI. After exciting the slides we want to image, you can actually get a signal at any point in time. But what what makes it or the type of kind of sequence we put into the machine will actually determine whether we are going to have a very good contrast or a very, very poor contrast. So pulse sequence is actually those steps we take, those series of steps we take before we finally get a signal. Mostly it involves RF excitation and acquisition of the image. These steps, all these two major steps, must always be applied in any pulse sequence we want to take. We first of all excite with RF. We tune it briefly for a period of time. Then we now go to the gradients. So we either turn the gradient on for a particular period of time, for a brief period of time, and so on and so forth. Then we acquire our image when we think we have gotten a maximum signal. Also, let's look at TE. What do we mean by TE? Time of echo. TE, echo time. Time of echo, TR. Repetition time. Repetition. Echo time. We are conversant with echo from sound or whatever. Echo is actually the signal we want to get. Echo. Echo denotes the signal, the measurable or the measured signal is the echo. So echo time is the time taken from the time we apply our RF pulse. The time we apply our RF pulse to the time we take signal, or the time we sample our signal. Let's use the word sample, the time sample. From the time we turn on our RF pulse to the time we sample our signal is the echo time. Whereas the repetition time is the time lapse between getting one signal and getting another signal. These things will become clearer as we move on from there, as we move on into the different type of signal. Echo time is just the time taken in turning on the RF pulse to the time the signal is sample. Whereas the repetition time, from the name repetition, is the time taken, but the time taken from one excitation to another excitation. So that's our repetition time, TR. And I believe we know that echo TE greatly influences our T2 weighting, whereas the repetition time greatly influences our T1 weighted images. You might want to know why. I think. So let's go to the main pulse sequence. Main pulse sequence. Okay, before then, let's look at basic pulse diagram. Basic pulse diagram. Everything we'll be doing under pulse sequence requires a kind of ability for us to understand or to depict what is happening at every point in time. Whether we are using inversion recovery, whether we are using spin echo sequence, or whether we are using gradient and recall the echo sequence. We need to know what is happening at each point in time. We need to be able to kind of diagrammatically sketch what is going on. Of course, you must have seen so many pulse sequence diagram. So at this, we're going to spend just a few moments looking at the basic constituent of every pulse sequence we are going to deal with them this morning. In all of them, we have, let me represent this, okay, because horizontal line. And first of all, we have to always apply okay. For simplicity's sake, let's start with a 90-degree pulse, RF pulse. It depends on how it is used. In some textbook, you might have the pulse sequence like this. Excuse me, let me answer this call. I think it's my colleague. Maybe she wants to also join one of our medical basics. Oh, I'm sorry about that. So we have these major steps. Okay, I said we could. Please, can we all mute? Can we all mute? Okay. Okay, thank you. So for some textbook, you might have the pulse sequence this way. It doesn't really matter. So we just have this as a pulse sequence. I mean, RF pulse. When we apply our RF pulse, let this one be the gradient, the orthogonal gradient coils. We represent this as slice select. This is for a phase, and this is for the frequency and gradient. When you apply the 90-degree pulse, you have to select this slide. This slide has to be selected. It has to be selected immediately you apply the 90-degree pulse. Because if you don't do that, the two of them are, the two steps are done simultaneously. If you don't do that, then one is actually doing nothing. You have to select the slides. Immediately you turn on the RF. Select the RF pulse. Then after that moment, you also need to turn on the phase and pose and gradient, the phase. Because the phase increases, let's use most times it is represented by a trapezium because the phases are different. Though in some textbook you might have them as a rectangle, but actually it is supposed to be a trapezium because the phases are different. The phases you can keep increasing from top here to the center, then it decreases that way. So you now also select you turn on the phase encode and gradient. Now the frequency encode and gradient, that is our readout, is going to be turned on when we want to sample the signal. We're going to turn on when we want to sample the signal. If you turn it on here, you are going to sample our signal at this point, which is not what we want. Because by introducing this slice select gradient, in fact, one thing that happens with the slice select gradient for all is that you also invert the polarity a little bit. We invert the polarity a little bit. And this is done such that when we are to read image out, it will be within the slice we are interested in. Because if we don't do that, we can actually move into another slide. So this is actually a kind of cancel the effect of this gradient you have applied to this pulse. But it is very, very necessary in the sense that we actually we are actually interested in this particular slice we have selected. So what happens? The gradient will be turned on. The frequency encoder gradient will be turned on at the time when we want to sample a signal, which is time TE. Let's say TE, which is centered on the TE. So when we're describing TE, when we were explaining TE to an when we're briefly introducing a TE, we said that TE is the time from the middle of this to when a sample is taken. So this is our TE for this diagram now. So when we sample this at a time when we turn on this gradient, this gradient. So that at this point, we are going to have a sample. This is basically what happens when we get to spin echo and gradient echo. We will get to understand this more. One thing we need to note here is for the phase encoding gradient, we have to iterate them so many times. This one fills one line in K space. The first one can fill a line in K space. We change the gradient, the phase encode gradient. for another set of TR, it is another line in case space and so on and so forth. For each time you apply this, each time you change the phase and code gradient, you're actually getting a new line in case space. So this thing continues on and on and on and on till continue changing. Each time you change, you're actually dealing with another case space. So this is actually a basic pulse sequence which we are going to encounter throughout our lecture today. Whether we are dealing with okay, before I wrap up, if you have any question at this time, I hope sequence diagram. I don't have any question at this point before we continue. Any question at this point? I hope you can all hear me. Hello?
Yes, sir, we can hear you, sir.
Yes, we can hear you. We can hear you, sir.
Okay. Thank you. Okay. So let's go to.
Hello, sir. Good morning, sir.
Yeah, good morning.
Sir, I just want more clarification based on the face encoding gradient.
Okay.
At what point it come on? Is it after the slide selection and the RF pulse is given, or is been towards when the echo, just like where we have the frequency encoded ingredient too?
Okay. Okay. No problem. Thank you very much for that. The slide select gradient is turned on after the slide select gradient has been turned on, because we want to apply changes to the face of the slice, to each portion of the slice. We want to apply a phase change, so that some points in the it's actually meant to localize. I mean, for spatial localization in this slide. Because if you don't turn it on, all we will get is all the slides. The slides we have selected, all of them will have um, the same type of a signal, or how do I put it? The same operation going on that slice. But that is not what we want to do. We want to be able to differentiate from each particular point in this slice. So if you don't do this, we are going to just be getting information from all the slides, applying the same frequency to the slide. But this one tells us that with application of this gradient, we are able to get gradations. I mean, different portions on the slides will have a different frequency, hence being able to spatially locate them. So this is actually turned on after the slides and select a gradient. Then when we get to spin echo and the gradient echo, I think it will become clearer. Nice. We want to look at the spin echo pulse sequence. What do we mean by spin? Of course, by spin, we are looking at how the spins of the hydrogen, of course, hydrogen atom is known as how this spins process, how the spin process, whether At a point in time, the spins might be this way, all of them. But as time goes on, immediately you apply your RF pulse. Okay, after application of the RF pulse, of course the RF pulse brings all of them to phase. Immediately you now switch off the RF pulse. We now begin to have kind of a defacing as time goes on. At the end, you'll not be fully defaced after some point in time. The spins will not be fully defaced. So this is key. If you don't put off the RF pulse, of course, you're not going to get any image. It is due to the fact that different tissues they relax at a different rate after the RF pulse has been exterminated. That is why we have contrast based on the way the spin orient, how they are oriented after we switch off RF pulse. So for spin echo, these are the basic diagram we have, the basic pulse sequence diagram. Let me just complete this short so that we just keep filling them. So for spin echo, spin echo normally uses 90-degree pulse. After you apply the spin echo, at the same time you select the slice. Select the slice, and this diagram is not just there. This diagram is not just there for fun. You can see this one is shorter than the first portion, the initial portion. It is so because at this one, the period for which we switch it on is approximately the 17 and 7, the time period for switching the RF pulse on, the 90-degree RF pulse. But this other inverting lobe, we now switch the other end of the slice gradient on the opposite polarity, such that this effect will, so to say, cancel the effect introduced by this one. But we don't want it to be a very long time. So that is why we apply it for a brief period of time, but slightly longer than this, so that the area of this is the same thing as the area of that, so that it has efficiently cancelled the effect of this. We might want to make it the same thing, but of course that will be spending unnecessarily a long time, which we don't want to do. So that is that. Then we now apply our gradient, our phase encode gradient for one iteration. Then from there, let's go to our frequency encode gradient. We want to sample our time. We want to sample this at a time TE. To sample it at the middle and TE. But one thing here is in between, this is our TE. So, these are T. In between TE, 90 degree, and TE, we need to introduce an inverting, a 180 degree pulse here, in between, halfway in between and TE, the time of echo, in fact, half TE. At the time half TE, we need to introduce a 180 degree RF pulse. If we do this, without this 180 degree pulse, we can simply get our image here. We can simply signal this thing here. Meeting is ending very soon. I have to log off, and then we log on with the same password. Without 180 degree, we can get our sample here straight off. But the signal here will not be very, very strong. We won't have a very, very strong signal. So that is why we need a 180 degree pulse to invert, to introduce what I need to explain here. We don't have two boards here, but let's just hold on. I want to log out now. I'll just log in also after about a minute. You can log in after about a minute.